Yeah, so first of all, thanks for everybody who's organizing this event. It has been great fun for me. I hope for you as well. I'm Helge Rodin. I'm an assistant professor here as well. Usually I'm in the office next to Alla, not these days. Yeah, so let's come to Alla. It's my pleasure to introduce Alla's talk. Alla is a researcher in computer graphics. She's most well known for her work on shape modeling and analysis. She has received a great amount of awards recently. I can't name them all, just the most recent ones. She was selected a fellow to the Royal Society of Canada. She is a fellow of IEEE. She is a member of the SIGGRAPH Academy, and she received the UBC Killiam Research Prize in 2019. So that was all in the last 1 or 2 years. Quite impressive. But yeah, let's talk about research and really things we can learn from. If I have to summarize Alla's work, she pairs really mathy things, really mathy theory in geometry with computational models of human perception and intent. Today, as I think she will talk about how difficult it is to learn human factors from data. I haven't seen her slides as well, so I'm excited as you. Let's welcome Alla, and yeah, I'm happy to listen to her talk on learning human perception of shape, identifying and processing available ground truth. Please go ahead, Alla.
Thank you, Helge. Let's see if my computer cooperates. Okay. So just setting it up.
It comes up.
Yes, okay, there we are.
We can't yet see the slides, at least on my side. Sometimes Zoom asks, kind of pauses the sharing. Maybe you have to press play again.
My computer just.
Maybe just stop and share again. So we have our little break.
Oh, Alla, you're muted.
1 second, everybody. Sorry.
Royce, we're good in time.
Okay. Let me try. Okay. Okay. No, just a sec. Okay. Shit. Sorry.
It was coming up, so I'm not sure.
Yeah. Really okay. Let me try it again.
It was saying screen sharing, but we couldn't see a picture.
Screen 1. Okay. Share. And now let me try it from here. Okay.
Yeah, it's coming up now.
Hi. Okay.
So we see your desktop now. Yeah. Now we see your slides. Perfect.
My slides.
Okay. So yeah, the stage is yours, Alla.
Okay. Thanks. Okay. Sorry for the lovely technical difficulties. I'll try to keep this entertaining since it's lunchtime and everybody probably is kind of tired. So just to position my work, when we talk about geometry processing, really a lot of what we think about is what's known as classical geometry processing. Problems such as how do you take a 3D shape and parameterize it into 2D, or how do you take a 3D shape and approximate it by a union of cuboidal objects, or how do you take, let's say, a 3D shape and decompose it into parts which are suitable for digital manufacturing. The common thing for all of this type of problems is that we know the mathematical goal. We know the metric we want to optimize, and our challenge is to find the solution subject to constraints or certain balance between competing objectives. But the key thing is we know how to measure what we want. As another example, for instance, if you take 2D image and you want to reconstruct the 3D object which corresponds to it, the common thing is repeatedly, we know what we want to optimize. So we have a very clear mathematical goal, and the challenge is to get there because those goals are typically pretty hard to achieve. However, a large part of geometry processing these days addresses problems which are somewhat less obvious. If you look at this raster image here, probably in your head, you immediately imagine the continuous counterpart. And that's a process known as vectorization. Here is a zoom on that image to help you a little bit. And I'm assuming by now, all of you have an idea in your head of what you want the continuous output to look like. probably this is kind of what you had in mind. Here's another type of similar problem. If I were to tell you, hey, I want an object which has the function of this green thing here, and I'm intentionally not naming it, and the style of this one here, again, in your head, you probably had imagined what you expect. Probably this is kind of what you had in mind. So if we think about these problems, this is what I mean by human-centered, as in we know intuitively as humans, when we look at those problem settings, we know what to expect. But if I were to ask you, okay, what is the mathematical function that we want to optimize in order to get here? Probably everybody would go, I have no clue. It's something which, my brain told me the answer, but I cannot necessarily explain why I reached that conclusion. So when we talk about human-centered geometry processing, these are the problems we have in mind. The big challenge here is beyond achieving the, solving for the optimization is understanding what do we want to optimize, which means we need to somehow capture human expectations, or in other words, to learn human perception of shapes. And the question is how to do it. And today I'll talk about what role machine learning can play in this space and what are the challenges in trying to use machine learning, which is why the answer from me is yes, it can play a role, but. And specifically, the big challenge that I'm going to try and describe here and maybe motivate a bunch of ML research is a challenge of identifying and processing the ground truth data which we can have available to us. Because obviously machine learning to a large degree depends, the ability of learning algorithms depends on the existence of ground truth. And let me talk about a bunch of different flavors of ground truth one can use in different contexts of human-centered geometry processing. So here is one example. So if you have those images on the left, can you imagine the 3D shape that those two sketches represent? And this is a very classical geometry processing problem, which had been around, I think, since the late 60s. How do we go from sketches to 3D models? Humans are incredibly good at these tasks. Computers, not so much. So the approach that this paper I was one of the co-authors on took was to learn from synthetic data. The idea was, well, if we have 3D models, we can use algorithms to generate synthetic sketches, and then we can learn the inverse relationship from a sketch to a model. And you can, I'm not going into the details here, but you can think about some kind of a composition of a network which does this process, and then use it. You can use that network to go from a 2D sketch to a 3D model. And you can get results which are pretty nice. So is that basically the answer? I mean, can we just use synthetic data? Because the good thing about synthetic data, it's easy to generate. We can have algorithms, for instance, which go from 3D to 2D, and we can generate as much or as little data as we want. There is a big problem, sadly. The data that you're going to generate this way is not going to look the same as what people actually use or draw. For instance, this is not a very likely human drawings. We just don't draw people this way, right? And this is the biggest weakness of synthetic approaches, is they are making certain assumptions about how people create content. And in order to, and those assumptions are often wrong, generating synthetic data, which is indistinguishable from human data, is equally hard to solving the inverse problem of using this data for training. So it's really not the same. Now, yes, sometimes what you can do, and I think to a degree what we did in this paper, is we can train the users. So instead of people drawing, spontaneously, they would do on their own, you can kind of try and teach them, here is how you draw so that our algorithm will now behave on your data. But that's definitely not ideal. What we would like is to learn what humans want from humans, rather than from algorithms that mimic what humans do. Because in order to do it right using algorithms, those algorithms really need to be indistinguishable from humans, and that's an inverse problem in itself. So what I would like us to look at is, how do we learn what humans want from humans? So here is an example. And to keep this entertaining, if you want to answer this question using your emojis, using the V and the X for the B or C, you can do it just to get a sense whether everybody here is on the same page. Which of the two shapes here, B or C, is stylistically more similar to the shape A? What do you think? Let's see if people actually want to participate and use the emojis. Do you have an opinion?
So yes is B and no is C, or what did you say?
Exactly. Yes is B, no is C, because we don't have B and C on the emojis. So let's see. I'll give everybody a second. Do you have an opinion? What's stylistically more similar to A? B or C? Yeah. Okay, let's see. Well, most people usually answer, I don't have here the stats from this particular response this time, but typically the answer would be B. And
8 to 1 here.
Yay. So this is a question which has many implications. For instance, if you want to search in a database for an object which has the same style as an example you have in mind in order to populate an environment, or as a starting point for construction. So this is a very practical question. It goes beyond just kind of a curiosity aspect. Now, what goes into this question? What's the challenge? Well, here's another triplet, A, B, and C. Which one do you think is stylistically more similar to A, B, or C? Again, same. Yes is B, no is C. And the challenge is that style transcends structure. I don't see many people here voting yet, but let's see. Let me give you a few seconds. What is stylistically more similar? Is B stylistically more similar to A, or C is stylistically more similar to A?
Things are running out, but it was something like, so more are saying C, 8 to 3 or something like this.
Yes,
was the biggest
I
number
agree with those who said C. But stylistically, C is more similar to A than B. Last exercise. Which of those two dressers is more similar to the bed? Dresser B, that would be yes, or dresser C, that would be no. Which of those dressers will fit better in your bedroom if that's the bed you have, and you have a budget to buy a dresser? Which one would you buy? B or C?
I only see B's.
B's, yes, I agree. I agree with the B's. So it's kind of a task that each one of us intuitively knows the answer to. The question is, how did you reach this conclusion? Why did we have consistent answers? And from an algorithmic perspective, how do we create an algorithm that enables us to answer this type of questions? And specifically, how do we compute a style distance metric between shapes, where the challenge, of course, is those shapes do not have exactly the same structure? How do we say that, yes, hey, this spoon and this knife are a perfect match? So we want to design a distance metric for that. And the question is, how do we collect data? And then how do we use that data? Because the first thing we want for something like this is to understand, what do people answer and how do we mimic them? And the approach we took in this work, and the approach is again, one of the kind of flavors of different ways of acquiring human data, is a style similarity study. So what we had is we asked a whole lot of people exactly the question I asked you all here. And anybody wants to also offer an opinion here, using your emojis, you can. So what we asked very formally was, which of the two objects on the bottom, B or C, is most similar style-wise to the object on the top? And humans are pretty good at answering this question. They have pretty strong opinions. So we have asked, as I said, a lot of people. This is the percentage of consistency. What's consistency? That's how many people agreed with the plurality response within every class of objects. Now, something to notice, you are not going to get 100% agreement, ever, partly because sometimes there are indeed ambiguous cases, partly because if you are running a large scale study, particularly in this case, we run it online on Mechanical Turk, you're going to have people who are just going to occasionally either make unintentional mistakes of clicking the wrong button, or some of them might just not care, some of them might not notice. So in general, if we want to look at collection of human data, we expect the consistency to be below, let's say below 95, typically below 90. But one of my pet peeves is when I'm looking at research papers which claims that their users had a 95% over agreement, because that only happens, I always joke, in the elections in the country I was born in, which is the Soviet Union. So 95% agreement is the Soviet elections. In typical collection of human data, this is kind of where you expect your numbers to be. Now, there's also an interesting comment here, which is there's a bit of a chicken and egg problem in collecting data, because if you don't have any idea on what people's answers are, well, for instance, if you're going to ask style questions like this, if you're going to throw in totally random objects where neither, for instance, is a dominant response, your respondent's accuracy will drop down. So in a way, even when you're collecting data, you need to a certain degree to have a balance of answers be kept roughly equal between B and C, because otherwise the accuracy of the respondents will go down. Intuitively, since we all grew up answering multiple choice questions in exams, we expect the distribution of answers to be roughly even. When it's not, our respondents get really upset and their quality of responses goes down. So in a way, in order to even learn from data, you already need to know something about that data, which is kind of just an interesting aside. Now, once we have the data, we can indeed learn a distance metric. And what kind of distance metric? Well, you can think about a combination of basis functions, which measure different features, and that those functions are combined through a range of parameters. Which features? Well, that's where understanding of the data comes in. And the key observation behind our method is that really when you look at style, what you're looking at is presence of similar style elements, which is salient elements which are recurrent and similarly shaped. Like for instance, something as in this illustration. So the way we use the learned data is given the input shapes, we detect those potentially matching elements, as in we do a segmentation of the 3D shapes, and then we measure the salience and the similarity of those elements. So what we end up doing is we end up optimizing this lovely function here. I won't go into the details of it, but the goal here is to match the confidence of the responses, so as to account for the fact that there will be questions where people have absolutely uniform, clear opinions versus ones where the opinion is a lot more fuzzy. And here are some results just to show that our algorithm really agrees with human perception. So the questions here were always given the object here, which is the one on the left, and those two, which is more similar. Green is our response, and the number is the percentage of respondents that chose that answer. So in this case, both our method and 70% of respondents agreed that this lovely little church here is more similar to this one over here, and 90% agreed that this column is more similar to this one than this. In terms of style, More interesting on very diverse structures, 90% of respondents, as well as our algorithm, thought that this very bizarre looking ceiling lamp is stylistically similar to this one, compared to this. So you can get pretty successful numbers. Here are the actual metrics. So this is the high level number. And as you can see, we are very much in alignment with the plurality in the same range or even slightly better than the human percentage distribution. So that's kind of the metric for success. You cannot expect to be much better than people. You can be maybe in the same range. So this gives you so what we had here is we combined this large scale preference study data with domain knowledge. Why do we need the domain knowledge? Because just the outputs of comparative studies do not necessarily give you enough information to obtain kind of a deep learned network, which is, let's say, featureless. So what we have seen here is comparative studies, I would argue, are usually would be preferable for synthetic data in the sense that you can still collect large scale data. And in contrast to synthetic, you know it will be fairly representative because you get input directly from humans rather than from an algorithm which tries to approximate the humans. The challenge, however, you need content. In this type of study, we could have that content because we were asking about similarity between existing shapes. In a lot of human kind of driven geometry processing, we want to create content. So we inherently don't have content to evaluate to start from. So that's a challenge. How can one address that? And this brings me to that example we have seen earlier of transferring style. So we have a target, we have a chair here, we have an example which gets a style. And what we would like is to get a chair in the style of the table. So probably something like that. If you think about it, this is a constrained optimization problem, where what we want is to have an object whose style is maximally close to the exemplar style. This part of it, we know how to measure because I've just described to you a style measurement. However, the second part is we want the output functionality to be the same as the target functionality. So somehow we need to impose a constraint on functionality without actually knowing what the functionality is, because we don't want to have a specific algorithm for chairs and a specific algorithm for beds and a specific algorithm for dressers. So style, we can rely on exactly the metric I have just discussed. But the question is, how do we address function? Because if we only use style, well, here is an output of our algorithm, which is stylistically, indeed, very reflective of this. I don't think you want to sit in this chair, do you? Probably not. So what we want is we want to preserve function, and the core idea was to constrain our edits to compatible edits, which is edits which retain functionality. Now, the question is, how do we learn it? And well, here we used a trick which sometimes works if you're really lucky. And the observation we made was that we can have some interesting ground truth data which is already available. What kind of data? Well, if you go online and you look at online databases of shapes, you'll find that those often contain entire families of objects in the same style. So you can, for instance, have a set of soft furniture which already has the same style, or the set of different lamps which again already have the same style. But now, since they have the same style, which is easily identifiable, you can now measure the relationship between the different style elements, as in, hey, this little piece of decoration can be used both on the top of a shelf and on the bottom of a table. So, hey, a top of a shelf can potentially be moved to be used as a bottom part on a table. Or, hey, this element and this element are identical, essentially identical. So that means that a leg of a bed can be nicely used as a leg of a chair without actually knowing that both are legs. So here the core idea is there is data out there which wasn't created for us, but the data already exists and we can use it. Once we do, now you can indeed learn from that data the relationship, the context in which you can or cannot replace certain parts, and then you can use that to obtain your results. So here are some eye candy, here are some results you can get. So here we take this style and transfer it to this object. So the style of the cream object applied to the functionality of the green. And so we get now a chair which matches this table, or a fork which matches this knife, or a cup that matches this sugar bowl. Now, something which is very important and just kind of emphasizing is when you are running an algorithm which is supposed to match human perception, you always want to validate the fact that it's not just you who think that your results are pretty, but you want to actually, I wanted to share a graph here, sorry. Screen here, yeah. You actually want to check that human observers agree with you. So we actually run a study which compares your outputs to, let's say, human generated ones and see whether users like yours about as on par, for instance, as the ones generated by a human, or you can test whether the objects you have are indeed functional. And again, in our case, we had users say, yes, the majority of the stuff you generate is functional. And this is just for comparison. When we showed them ground truth objects, which is stuff generated by professional modelers, they said that 90% of it is functional. So our method has pretty similar performance. And again, you cannot expect 100% results. So even though this stuff was generated by modelers, so we can actually say with certainty, it is supposed to be functional. When you ask human observers, you get an uncertainty interval. So here, this brings us to this one more idea of how can we learn from humans. If we have pre-existing data, we are incredibly lucky. It's very representative, it's excellent, you can learn from it. Problem, most of the time, we don't have it. So what else can we do? And this brings me to this last example, which is the clip-up vectorization I mentioned earlier. So the challenge we are addressing is we want to go from raster images to their continuous representations that humans have in mind when they see those objects. So here is a raster, and here is a vectorization we seek to get. And again, the success metric is consistency with human expectation. Here is your input. Here are 4 outputs from 4 different methods. I'm not going to ask you to use emojis to choose which one you think is the right one, but you can think which of those 4 is the one you would expect to be the vector result if you have given this raster. So the one here is the one created by our algorithm, and a bunch over here are a different commercial algorithms out there. So how do we learn how to create this type of vectorizations? Well, the first idea would be, hey, why don't we use just pairs of raster and vector images? We have raster, we want to create vector. Well, let's just use pairs of data. The question is, what pairs? Well, first idea, let's take vector images. We have lots of vector images, rasterize them, and then try to learn the vector from the raster. And now let's think, is that a good idea? First thing that comes to mind, probably everybody here heard about the Nyquist theorem, right? And the fact that when we rasterize, the rasterization is inherently lossy. So inverting an inherently lossy problem can be a bit of a challenge. However, there is a bigger problem. Here is a vector input I'm not showing yet, and here is its rasterization. Can you imagine what is the vector you as an observer would like to get as output if you invert the process? So this is your raster. What should the vector be? Well, here is the vector that was used to generate this raster. And you have realized that in the rasterization process, we lovingly lost those rounded corners. And as a viewer, if I were to give you this as output, given this raster, that would be an unexpected and counterintuitive result. So no, this is not really an option. Even though there's lots of data like that, we cannot use it because it's not going to give us what the viewers expect. An alternative could be, well, how about we hire artists to generate vectorization? That would be wonderful, except it does not scale. It takes a professional 30 to 45 minutes to generate a single vectorization. You can think about how many of those you would want if you wanted to have training data for an algorithm that does this process automatically. So we really need some kind of data which is a lot less expensive to generate and where we need very little of it. So the core idea in the work we had was to combine perception priors, namely what we know about human perception, things like Gestalt psychology and other sources, with compact human input. And the key bit here is also we want very little input, and we want that input to be collectible from non-experts, because collecting expert input is hard. The challenge is, how do we minimize the amount of input while still being able to learn what we want? And the perceptual cues we use are the following. So if you have a raster, we know from observations about human perception is that people expect the vector to be accurate. Namely, they expect it to be very close to the raster. How close, that's another question. But given choices which are more or less accurate, people tend to prefer the more accurate one in many cases. Another perceptual cue, which comes from Gestalt psychology, is that humans prefer simple explanations. So for instance, if you see something which is straight and has 90-degree angles, you want the vector to retain those properties. You want simplicity. And another cue we also know from psychology research, people like continuous and smooth shapes. So given something which is less continuous and has corners, and something which is more continuous, they tend to prefer more continuous. Lastly, in the same context as simplicity, given, let's say, things, outputs which are more regular, for instance, more symmetric, humans like symmetry, we like regularity. The challenge is that those principles conflict. So here is a raster, here's another raster. Again, I'm assuming in your head you have just imagined what you would like to get. However, I'm assuming that for this raster here, you probably prefer this. Well, for this raster here, you prefer this one. However, notice that these two are more regular and more simple than those two. In contrast, those two are more continuous. So the challenge is that we need to somehow balance our cues. So this is accurate and simple and regular. This is slightly less accurate, but more continuous. Somehow, as humans, we prefer those two rather than preferring a single column. And where the learning algorithm for us comes in is in learning how to balance those cues. So, and in a way, by having those cues in the system, we reduce the complexity of the problem we want to learn. Because instead of learning totally going from here to here as a single step, we have the cues and we have the corresponding features which encode those cues. So what we need to learn is the impact of those features. And what we have done in this case, we had used two hybrid approaches. In the more early paper, which was 2018, what we had is we had humans annotate corners, namely C0 discontinuities on the raster. And then we had an algorithm which learns those corners. And once those corners were there, we have done spline fitting. So the data was manual corner annotations, which is already much easier to collect than complete vectorizations. In a more recent work, which had shown superior results, we took a slightly different approach where we broke our problem of vectorization into 2 steps. The first one was to approximate this shape with a polygon. And the key observation here was that in order to do this, we don't actually need learning. Because the problem domain is much more restricted, we could just directly use the perceptual cues or a balance of those cues to obtain results, which were very much consistent with what people would get. And then our learning was really focused on this step here. And in particular, we really limited the learning to the question of, given a pair of edges on a polygon, what should the fitted vector curve be? Where you have 3 options, which are illustrated here. And those are the 3 options we wanted our classifier to literally tell us. One is you just keep your corner as is because it should be sharp. You fit your corner using a single smooth curve. This is the case here. Or you fit your corner given a combination of a smooth curve and a straight line. Notice that now we have a much more simple problem, and one where we can use the learning algorithm with a very small set of features. So literally, this is our entire set of features, and we can train this model successfully on just 23 input images. So it's really, really tiny training set, which is much more feasible to create than collecting, let's say, hundreds or thousands of manual vectorizations. And here's a comparison. So this is the most recent method. This is the one from 2018. And this is what's currently used in commercial software. So you can see that we're really preserving the simple features that humans expect you to preserve, like everywhere here, while rounding the stuff that a human observer would expect to get rounded, which is kind of the ultimate goal here. So to summarize, and before, again, as a reminder to me, we always need validation. Yes, I showed you a pretty picture. Do human observers agree with my pretty pictures? The answer is yes. So the green here, the blue here is us. Orange is both methods. Green is the other method. Pink is neither. So again, we asked people using that format you've already seen me use in this talk over and over. Here is an input. Which of those 2 is more consistent with the vectorization that you would expect to get? And our method had been consistently preferred over all prior alternatives. So in this example, I've shown yet another version of how we can try and learn from humans given the challenges of obtaining data. And this is annotation rather than content. So the idea is to reduce the problem of, let's say, humans creating content, which is very time consuming, to one of annotation of content, which is kind of has many parallels to the comparative studies. So you ask the human to do a very easy task, but one which is representative of the data you are trying to collect. The challenge still is, it's still time consuming to generate at scale. So we can hope for getting, let's say, as I said, in this paper, we literally were able to use annotations from 23 inputs. In many cases, you probably need a lot more. So the question is, again, how do you collect annotation? Because you are not going to be able to collect thousands of annotations. That's still a time-consuming task relatively. So you want to still think about how do we have data efficiency? So if I look at take-home message for me, kind of the stuff I would like machine learning experts here to think about in how they can help, let's say, the type of problems that we look at when we look at human-centered geometry processing is, again, kind of at a high level, the success is measured as alignment with humans, not with synthetic data, but actually with what humans expect. We don't want to reinvent the wheel. If we have domain knowledge and perception research, we want to use those. Because if we don't, then the problems will likely be untractable. The challenge is identifying or collecting reliable data is really, really hard. So thinking about how to collect data is a big part of the problem. And then from a machine learning perspective, the challenge is to learn from this data, which is sparse. We don't have a lot of it. And it's often indirect. For instance, in the ideal world, I would have loved to learn from raster inputs and their vectorizations, but those are impossible to collect. So the data we are going to have is very often data which tells us something about the answer we want, but it's not going to give you the full picture. So if I think about what would I like to ask machine learning people here, what's my ask is, I want people to think more about data limited learning. As in, how can you make algorithms which will enable people like me to learn from data, from the type of data that we have? In particular, something I would really like to have is imperfect answers, which means, for instance, if I have a classifier, I would like my classifier to say, on this data, the confident answer is yes. On this data, the confident answer is no. On this data, I have no clue. Because if I have that no clue, or if I have this metric of accuracy or confidence, I can incorporate it into my methods. When a machine learning algorithm gives me a yes or a no, it's often not very useful. It's kind of related to the comment that Purang made earlier, is I would like my ML to tell me when it doesn't know. It would be extremely valuable. In the same context, instead of giving me a single solution, for instance, for a generational problem, like a GAN, I would like to get, instead of the algorithm giving me one solution that the algorithm thinks it's perfect, if the machine learning can generate for me 10 or 20 solutions, which are kind of okay, I can take over afterwards. As a human, as an observer, I can also very easily pick among those. So I would like tools to give me answers with imperfect data, because I'm not going to have ever a lot of data. And also kind of something to mention is a lot of the problems we are solving because are very hard at the global level. And what we are doing is we are looking at them locally. Like the reason we can look at, for instance, 23 inputs is 23 complete drawings contain a lot of edges on the boundaries. So we can have pretty good, reasonable amounts of local data, but that means we have a classifier or some other learning tool which is operating using only local features or local information. The reason we cannot feed it directly global information is just because we don't have enough global examples or enough variants of those. It would be very interesting for me to see if there are ways to somehow go from local to global in a principled way in the machine learning lab. Okay. Thank you.
Thanks a lot, Alla. Do we have questions from the audience? There was actually a comment by Sonny in the chat early on when you were asking for the response. I think it was even your first example. And the comment was, C and I'm Asian. So how do you incorporate this kind of context, social norms, different people from different parts of the world?
Perfect answer, yes. This is a question I'm always asked about. Yes, the style one is very interesting because different people have slightly different perceptions of style. So see, I'm assuming you notice the building on the top is a Japanese temple, while the building on the right was, I think, a Chinese temple, pagoda. And the building on the left was, if I remember, a Gothic cathedral. Yes, style sensitivity differs across culture. Now, it's very interesting. I have done this talk across multiple countries. Typically, there is more divergence in different spaces, but in general, that's why, again, we look at plurality, right? So that's why the goal is, yes, individuals on many questions, you would find people who would argue otherwise, but our goal here is to match plurality, which of course, again, introduces its own challenges, right? Because you want to ask, okay, if some people have different opinions, how do you incorporate it? That's also where my comment about accuracy relates very much. As in, for instance, if an answer to a question is more fuzzy, I would ideally like to incorporate into my method, right? As in, half the people think this, half the people think that, there's a divergence. How do I incorporate it into my algorithm? If the ML can give me an accounting for the divergence, that would be great. Okay.
Thanks a lot. There was a comment by Ed in the channel, very somewhat off topic, but he's commenting on measuring, human expectations, and he's seen that in arts, the grades given to students are actually much lower than in computer science, for instance, where there is one answer. Seems to be the case also elsewhere. That's interesting to know, and it might be actually the right conclusion. Yeah.
Yeah, exactly. So some of the space we are dealing with is the fuzziness. That's why I would like fuzzy learning, right? As in, I want certain bounds on confidence, because that would help a lot in being able to generate stuff which is consistent with what people want. Because there are some things everybody wants, there are some things that only some people want, and there's a bunch of fuzzy areas. So, yeah, so fuzziness is built in. And I see that Kevin has a question.
Yeah. Do you want to go ahead?
Yeah, I guess a comment and a question. The comment is, sounds like you're a closet Bayesian, right? All of this desire for uncertainty estimates. So you should get talking to the statisticians. I think your talk and Trevor's are nice bookends to each other.
Okay, that was my hope. That's why I gave this talk, right? I was okay. Hey, I want people to talk to me.
Indeed,
because I have problems for them.
So I like the way you kind of articulated the boundary between what the where ML helped you and where you had to bring a lot of expert knowledge to effectively run a learning pipeline yourself. I guess something I was left wondering that might sort of help to situate your talk in the context of this event is leaving aside all of the breakthroughs, sort of holding constant all of the sort of state of the art in graphics and HCI and all the other kind of pieces that you were using, and looking really just at the interface between your work and kind of AI ML. I wonder, how would your work have been different 10 or 20 years ago? What are you leveraging from kind of modern ML that you wouldn't have been able to use 10 or 20 years ago? And how do you imagine your work might be different 10 or 20 years in the future if AI ML were to improve?
So I actually had a slide which I took out. So 20 years ago, the way people in computer graphics judged the success of their papers was by, hey, as an author, I really like those pictures, and so do my reviewers. Now, I think there's a lot more.
I would call it a breakthrough in kind of graphics HCI, though. I guess I'm wondering specifically, like, yes, holding that to today's state of the art. Where's the, are there ways in which your work is really dependent on kind of relatively recent breakthroughs in AI ML?
So recent breakthroughs, I'm not sure. As I said, this is kind of what I want. This is the stuff that's missing for me. So I can say what I want. I mean, I think in terms of what I can do is, yes, I can have more. I think that the ease for me actually is not that much the ML, but it's my ability to actually collect human data. So something like Mechanical Turk for me made a huge difference, which is not exactly answering your question. And then the methods I'm using things like random forests, which had existed for a while, right? I mean, random forests are not a statistical breakthrough of the last 5 years. What I really am missing is this, as in, if I can have methods which knowingly operate on small data, so not your 10 million inputs, because I'm not going to ever have 10 million inputs, but knowingly operate on small data and that are aware of their own limitations. So I want, as you said, Bayesian, right? I want answers which are uncertain. Because right now, the ML methods that are out there give me a single confident answer, which I don't know how to quantify their confidence. So that, I think, for me would be the biggest one. The other one would be operating on irregular structured data. Again, a lot of the current ML works wonderfully on images because they have pixels which have very fixed connectivity, or voxels which have a very fixed connectivity. My data has irregular connectivity. And that's another one where there is some methods in that space, but I am yet to see them applicable to what I'm working
Awesome. I see Robert, you switched on your video. Do you have a question or just chiming in? All right. Yeah, I think then we satisfied all the questions. Thanks a lot, Alla, again. Let's give her and all speakers an applause.